Now we are going to start with the last talk of today's session, that is our National Mathematics Day session. And as Professor B.S. Chowdhury has not, is stuck somewhere on the road, and so I have to chair this session. So let me introduce the speaker. Professor Roychowdhury is a full professor at the University of Texas at Rio Grande Valley. Dr. Chowdhury's current research areas are quantization theory and applications, then fractal geometry and dynamical systems. He has over 45 publications in peer-reviewed refereed journals. Many of them are published in well-known journals such as Israel Journal of Mathematics, Proceedings of AMS, Fundamenta Mathematica, Journal of Mathematical Analysis and Applications, Journal of Modern Dynamics, Kyoto Journal of Mathematics, etc. For the work in quantization theory in the year 2014, for 2 years, Dr. Chowdhury was awarded research grant from US National Security Agency, NSA. So really, we are very great that Professor Roychowdhury has accepted our invitation and he is here with us. So I don't want to be in between our audience and him. So I am giving over the mic to Professor Chowdhury to present his talk. Over to Professor Roychowdhury.
Yes. So, okay, so I don't know how to share this.
Okay. You have not handled earlier Google?
No, we use always Zoom.
Okay. So there is an arrow on the right hand side. In between, you will find an arrow, upward arrow.
Upward arrow, yes.
You click that one.
Oh, okay, then
you are getting three either window and so where it is, your presentation is there. Window. So select the window. You may get that one.
Okay, share.
And then share.
Okay, share is not highlighted. Okay, let me see.
Sir, actually, when you will click on that window, then share will highlight the window which you want to present If you'll click on that window, then
okay.
Yes, sir. Okay. Thank you, sir, and good evening, sir.
It's full screen mode. Is it coming now?
No, sir.
Not yet. Maybe it will come. Let me check.
Sir, you can share your entire screen.
Share now.
Yes, it is coming. It is coming.
Okay.
Now full screen can.
Full screen. Okay.
It's okay. Fine.
Yes.
Very
fine,
good.
sir.
Okay. So I can start, right?
Yes.
First, I would like to thank Professor Shom and other organizers for giving me an opportunity to talk here. So the title of my talk is Quantization for Probability Distributions. And so this talk, I am not going to tell a lot of deep details. It will be basic talks so that everybody can understand from any background. And so what is quantization means? So quantization is the process of constraining an input from a continuous or otherwise large set of values, such as real numbers, to a discrete set of integers. What does it mean? So you can see the input is coming from a continuous or a very large set, and output is a discrete set, and which contains smaller number of values. So it has broad applications. For example, in data compression, see that lots of points are coming. You are representing as a discrete set, and also in signal processing. A good application of quantization is it has lots of real life problems. For example, in mobile tower technology, for example, suppose in your state you would like to install and say 3 or 4, suppose I'm saying 3 mobile towers. And we know the signal of the cell phones depends how far you are from the tower. If the other conditions like the weather and everything is even same, so signal completely depends how far you are from the tower. When the so our goal in quantization theory is to find the best locations of the towers, so that if you move around in your state, I'm talking about the state, not the country or any other thing, just in your state, say suppose in UP or say Delhi, like this, and if you what are the best locations of the towers, so that if you move around your state, you can get the best signal in your cell phones. Even the electrical engineers, they do not know what are the best locations, but they try to guess by some algorithms. In quantization theory, our goal is to find the exact locations of the towers, so that if we move around, we can get the best signals in our cell phones. In quantization, people can work from many different directions, and I'm going to talk about on quantization of probability distributions. So what is the so here I'm going to tell you the basic definitions first. Let P be a bold probability measure on RD equipped with a metric. So what is our goal? To represent the support of P by a finite set of points. So what is support of P? So when an unbiased die is thrown one time, then P is a bold probability measure on the real line. And support of P contains 1, 2, 3, 4, 5, 6. You see that P is a bold probability measure on the real line, but here support of P contains this, and probability of which is unbiased 1 over 6, 1 over 6, 1 over 6, like this. When an unbiased coin is tossed 2 times, then P is a bold probability measure on R square. So unbiased coin, suppose one side is head, head means 1 and tail means 2. So it can come 1, 1, 1, 2, 2, 1, 2, 2. So here P is a bold probability measure on R square, support of P this. When P is uniform distribution on the interval 0, 1, then P is a bold probability measure on R, and here support of P is the closed interval 0, 1. So in quantization theory, our goal again is to represent the support of P by less number of points. Suppose here, for example, here our goal is to represent support of P by less number of points. For example, suppose support of P contains these 6 elements, 1, 2, 3, 4, when it die is thrown, and we'd like to represent this support of P by 2. So this is a data compression. So you have, so in the original set you have 6 points, and you are going to represent suppose by these 2 points. One is 2, other is 5.5. Then how to calculate? The calculation, the error is calculated by the expected squared Euclidean distance. So we are taking this metric, Euclidean distance, then we are taking this square to calculate our error. So in this case, the error is P. P is the probability, and we are representing the support of P by the set alpha. Alpha is these 2 points. So this is the error. In the case of continuous, we calculate this means this one. Of course, in statistics, any probability statistics book, you'll see. For the continuous case, integration comes, and for discrete case, sum is coming. So in our case, it is discrete, so we are using this formula. So here is the error. So minimum. So if you represent so 1, now you have you are represent these 6 points by these 2 points. So if it is 1, so which one it will represent? 2, because 2 is closest to 1. See that 1 minus 2 is square, and we are getting probability 1 over 6. Then 2 is represented, of course, by 2. This, and 3 is represented by closest point is 2, and 4 is represented by closest point is 5.5. This is the formula. This is the error. And now suppose if you want to represent these sets support of P by 2 points, 2,5, then the error is this much. Now look, which one is the error? Smallest error. This one is smallest error. So we can say the error depends on the points, how you are choosing them, and also on the distance that you on the metric that you are choosing. Okay. A set of 2 points for which the infimum of the errors occur is called an optimal set of 2 means. So our goal is to find these 2 points for which the error is smallest, and the corresponding error, that is smallest error, is called the quantization error for 2 means. Now I am going to give you the general definition. Quantization error. So RD, any space, so D is greater than or equal to 1. So alpha be a finite set, and take any number R, 0 to infinity, any finite positive real number. Then the cost of distortion error for P. So now suppose if you want to represent the support of P by this point, by the set alpha, then this is the formula. Previously I gave you the example. Now here is the general definition R. So in the previous case, we have taken R equal to 2. So in our case, R is any positive real number. So this means this one, and this is this one. So if you represent the support of P by this K points, then error is this one. So what is this? So if you use this formula, I'm using integration because if you, of course, you can use this one also if it is discrete. And so AJ is the set of all points. So AJ is the boundary region of AJ. What does it mean? A1 means set of all points in the space which are closest to A1. So A2, big A2 is the set of all points which are closest to small A2. So we can separate the integration like this way. K integrations are coming. So this is the error formula. So error depends on what here? On the set alpha, also on R, also on the metric. So the error depends on three things: metric, the power R, and also the set, how you're choosing the points. So what is nth quantization error? So nth quantization error is the smallest error. See that we can choose alpha in many different ways, and we are taking this infimum of all these errors. That is called the quantization error. So now, is there any set alpha for which the infimum exists? We are always assuming expected or rth moment is always finite. If this is true, then there is some set alpha for which this infimum exists. That is, we can replace infimum by minimum. And that set alpha is called an optimal set of n means for P. And the smallest error is called the quantization error. Okay, now how to do this in real life? Suppose this is your region. And you'd like to install, say, represent this by 3 towers. Say, we are going to install, say, 3 towers. Or it is same thing as, suppose you'd like to represent this space by the 3 points only, the set of all points in this region by 3 points. So these 3 points are there. First you choose the 3 points, of course, A1, A2, and A3. After you have chosen it, you take the perpendicular bisector of this, you join this, take the perpendicular bisector, and join these 2 points, take the perpendicular bisector. Of course, then they coincide at a point. So this is called the boundary region of A1. This is the boundary region of A2. So now, if your cell phone is in this region, suppose this is your state, and you're moving around, you can go anywhere. You're free to go anywhere. Suppose your cell phone is here. Of course, your cell phone lies with you. So you are moving means your cell phone is moving. Suppose your cell phone is in this region, then this is the tower. It will catch the signal. If you're here, it will catch the signal here, catch A3. Now, suppose you're in the boundary. If you are boundary, then this tower can catch the signal or this tower. That's why sometimes you'll get cross signal, but it happens rarely. This is a narrow line. So cross signal comes, suppose if everything is fine, some cross signal comes because 2 towers are fighting with each other. That's why sometimes you get disconnect or your signal bars changes from 4 bar to 5 bar like this. Okay. So our goal is to find the 3 towers so that the error that I gave you the definition of error is the smallest. Now, there are 3 things. Points in an optimal set are the conditional expectation in their own boundary region. Suppose these 3 points are the optimal locations, that means error is smallest. Then A1 must be the conditional expectation in its own region. A2 must be the conditional expectation in its own region. Here it is. Here is the definition of conditional expectation. See, if A1, A2, A3 are the optimal locations of the 3 towers, we must have A1 equal to conditional expectation. And this is the definition. Any question from anybody up to this? Similar is the expression for A2 and A3. But so
why are you finding the measure of location?
Okay. Now our goal, which measure of locations? Because there is a probability.
Yeah, I mean.
Because the probability is located. Because the points are not because there is a probability. Probability is defined on this. So suppose what is the probability that you are choosing X? Suppose you are in this location. That's why P is coming. The probability is coming here, expected, because we are not sure, because it is probability is associated, and some probability can be uniform, maybe biased, maybe one side is more probability, other side is less probability. So probability is giving us the importance of the location, right? For example, when you are putting the mobile tower, suppose in UP you are putting the mobile towers. Always our goal is to install the mobile towers where more people are living, right? Not in the remote areas. So that means importance are given by the probability. That's the probability is coming.
That
For example, suppose our region is like this, and we are considering, say, uniform distribution. So in uniform means, of course, any place the probability is same. Okay. Now look, let us divide this region. This is diagonal. So A is the average in this location, B is the average in this location. Now we calculate the error. Okay. Also here in this case, we can divide in the middle. I'm saying uniform distribution. So we need to represent by 2 points. It's the square. So divide in the middle. Then we take the average here. We take the average here. So both of them here, A is the conditional expectation in this region, B is the conditional expectation in this region. Also in this case, A is the conditional expectation here, B is the conditional expectation here. But this one gives smallest error. So this is the optimal locations, not this one. That's why I'm saying converse is not true. If they're optimal locations, they must be the conditional expectations. But if they're conditional expectations, that does not mean that they are optimal locations. Here you see, in both figures, the 2 points are the conditional expectations in their own boundary regions, but the second figure gives the optimal location of the 2 towers. Question? Okay. Next. Now, so you understand now what are the optimal, how optimal locations comes and properties, and what is the quantization error. Now, what is quantization dimension? Okay. Of course, our goal is to represent the support of P by finite number of points. Of course, if you increase the number of points, representative points, then the error will decrease. Suppose you have, say, 100 data set and you're representing by 2 points, only 2 points, then, and sometimes suppose you represent by 5 points. Of course, if you represent them by 5 points, that will be, error will be smaller because you are giving more information. So if the number of points increases, then now I'm drawing a graph. This is the error, and this gives the points. So see that here. If you increase the number of points when you're representing it, then the error is decreasing. Here also error is decreasing, but in this case, error curve is going to decrease faster than here. Here also error decreasing, but slowly. So quantization dimension gives you the speed, how fast the error goes to 0. So this is the formula: DRP limit R log n minus log V n RP. Now we know the quantization error depends on the metric, on the R, and how you are choosing. So metric R. Okay. Now quantization dimension does not depend on the metric, but quantization dimension depends on R in some cases. Let me tell you here. Here is some observation. Nth quantization error for any positive integer n depends on the metric and also on R. Quantization dimension never depends on the metric. Does it depend on R? For an absolutely continuous probability measure, quantization dimension equals to the dimension of the underlying object. It does not depend on R. But, for example, the quantization dimension of uniform distribution defined on the line segment, circles, squares, and hexagon are equal to 1 because they are all dimension 1. For some details, one can see Joseph Rosenblatt and M.K. Roychowdhury's paper, Uniform Distribution on Curves and Quantization. Here is the, but there are some exceptions. For a singular continuous probability measure, for example, for a probability measure supported on a fractal, the quantization dimension depends on R. Because of that, it is highly interesting to investigate the quantization dimension for the probability measures supported by fractals. So quantization dimension for an absolutely continuous probability measure is not interesting at all. But quantization dimension for fractal probability measure is very interesting. Now, quantization dimension also connected with other dimensions of dynamical systems like Hausdorff and packing. Let me wait a second. Okay, what is quantization coefficient? For any S, any positive real number, the numbers this and this are called the S-dimensional lower and upper quantization coefficients for P of order R. It can be shown that if you can, of course, limit infimum is less than equal to limit supremum. If you can show limit infimum and limit supremum are finite and positive, then this S is equal to quantization dimension. So there is another formula to define calculate quantization dimension. Connection with other dimensions. Hausdorff dimension of a probability measure is always lies between, okay, sometimes quantization dimension exists, sometimes does not exist. If the quantization dimension does not exist, then we calculate lower quantization dimension, which is limit infimum, and upper quantization dimension. So always lower quantization dimension lies between Hausdorff dimension and lower box counting dimension. On the other hand, upper quantization dimension lies between packing dimension of the measure and upper box dimension of the probability measure. Question on this? Okay. Can you see? Okay, let me say.
I have one question.
Yes.
Is there relation with dimension of its support? P is a measure and it has some support. So
Yes.
whether it is related to fractal dimension or Hausdorff dimension of support of the measure.
Yeah, of course, support is important. We do not care about the other things. Of course, when you say the dimension of the probability is, yes, it is connected with the support. Support is the important things, because other things, probability is 0. Yes, it makes sense. Can you see the screen, local dimension, quantization dimension of dynamical systems I'm showing?
Yes, sir. Yes, sir.
Yes. So here you will see, this was published in Journal of Geometric Analysis, and here you will see the defined connections with different other dimensions of dynamical systems. And also we have defined here what is the difference, what is the lower and upper Hausdorff dimensions of probability measure, what is the definition of lower and upper Hausdorff, and lower and upper packing dimensions of the probability measure. Okay.
Hello.
So yes, question.
Yeah,
Any
Subhash
question?
this side. Hello, sir. Good evening.
Yes, good evening.
Sir, I have one question. Like,
Yes.
it is application-based question.
Yes.
Like, if we are going to reduce error, or we are going to reduce, like, if dimension is very less, then condition will be very optimal. Like, our purpose is to reduce
Yes. Yes.
quantization dimension or quantization error.
Yeah, if the quantity dimension is low, that means error will go faster.
Faster. So that
Yes,
means
the error curve will be faster. It's going to 0 slowly, yeah, quickly.
yes, sir. So that means.
So, for example, yeah, in this case, quantity dimension is smaller. Here it is high. Thank you for asking. Makes sense?
Sir, yeah, actually, I have not completed my question.
Yes.
So that means our purpose is to reduce, find a lower dimension, lower quantization dimension.
Yes.
And we have a relation between Hausdorff dimension and quantization dimension. And
Yes.
we have many many techniques to find lower Hausdorff dimension.
Yes.
Like mass distribution method, Fourier transform method, to
Yes.
compute lower bound of Hausdorff dimension.
Yes.
So when we want to calculate packing dimension, lower bound of packing dimension, then we
Yes.
have different technique, or
Yes.
we can use that technique also for this.
Yes.
So because our purpose is to reduce quantization dimension. Are you getting, sir?
Yes. 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 Our purpose, of course. Okay. One thing, let me tell you. Suppose if your probability is fixed, then quantization dimension is also lower and upper quantization dimension is also fixed, because we are defining for the probability measure.
Yes, sir.
Makes sense?
Yes, sir.
Because yes, so our goal is to define the quantization dimension. We are defining it for the probability measure, not for the set. Quantization dimension is defined for the probability P only. So if P is fixed, quantization dimension is fixed. Of course, it depends on R.
Yes, sir.
If you vary R, then it will be maybe more, maybe less. Make sense?
Yeah. Yes, sir. Okay.
Okay.
Thank you, sir.
Yes. Now the interesting thing, people can work on quantization dimension. It is easier to work in quantization dimension, but to find the set optimal locations, optimal points are extremely difficult. In some cases, we have calculated this. I'm going to tell you some examples in this case. Look at that here. It is not necessary to know optimal sets to calculate the quantization dimension. For example, let us take this set C, 1, 1, 2, 1, 3, 1, 4, and let us take the probability measure P is like this. So probability of 1 is 1/2, 1/2 square, 1/2 cube, like this probability is defining. And our goal is now to find the quantization dimension. So take beta like this, take any set. So then the error for this set, we calculate this much. Then what is Bn? Bn is the smallest error. So this is the error for a set of n points, this much. So Bn is the smallest of all the errors. So Bn must be less than or equal to this one. Now, so quantization dimension of P is equal to, this is the formula.
Yeah.
This is, yes, makes sense? So this is less than or equal to, see that now you put the values here, less than or equal to this, which is goes to 0. Now you can use squeeze theorem, which means quantization dimension of P is 0. But you see that here we do not need to find the optimal locations, optimal points. But we can easily calculate the quantization dimension. There are many papers in the market for calculating for quantization dimension for different fractal probability measures. But still there are many unsolved problems. Okay. Now, Quantization dimension of self-similar measure. First graph and Lewis, it was quantization was known to electrical engineers for last several decades, but it was introduced in mathematics in by Graf and Lewis in Germany around 2000, around the year 2000. What they did first, they did quantization dimension for self-similar measure. I'm going to show you what techniques they used. Let Sj be contractive similarity mappings on Rd with similarity ratios Sj, satisfying the open set condition. So what is open set condition? Of course, we know, but still I'm going to. Open set condition means there exists a bounded non-empty open set O subset of Rd such that union of Sjo is subset of O and their intersection of Si Sjo is empty is a wait. It should be empty set, not equal to. It is empty for open set condition. That is the children's. That is when you're applying the mapping, they are not overlapping. So it should be equal to empty set, not equal. That's a typo. Now, if P1, P2, Pn is a probability vector, then we know mu is self-similar measure. This is called self-similar measure, and they calculate the quantization dimension. See that how? Let kappa be the kappa is a positive number such that which satisfies this condition. Okay. If P1, P2, Pn is equal to this one, then quantization dimension is equal to kappa, which is D, which is the similarity dimension. If P1, P2, Pn, this probability vector is not equal to this one, then the quantization dimension is this kappa. They first showed it. Graf-Lewski. Then in 2009, see that after 2009, I generalized the results of Graf and Lewski, and I determined the quantization dimension for ergodic measure with bounded distortion. How we did? This is the general technique. Let Sj be contractive similarity mappings on Rd with similarity ratios Sj, satisfying the open set condition. Let E be the unique, non-empty, compact subset of Rd, such that, of course, E is the attractor or invariant set. And sigma, we are defining like this. For sigma, this is a word of length k. S sigma is the composition mapping. So E sigma is this. Let mu be a Borel probability measure on Rd, satisfying the bounded distortion property. What does it mean? That means for any two words, sigma tau, then k inverse mu S sigma E, mu S tau E is less than equal to mu S sigma tau E, k of mu S sigma S tau E. Now, if k equal to 1, this case reduces to the self-similar measure, like Graf-Lewski discussed before. Now we are defining a pressure function PQT. In multifactorial analysis, there is a pressure function always that arises in thermodynamic formalism. A pressure function PQT we define like this way. Limit k goes to infinity 1 over k log mu E omega q S omega t, which is continuous, strictly decreasing, and convex in each variable separately. Moreover, for a given q, we always get limit t goes to plus infinity PQT is minus infinity, and limit t goes to minus infinity PQT is plus infinity. So this is the curve. So PQT, notice that for a given q, this is a PQT curve. For a given q, there exists a unique t, which is beta q we are defining, for which PQ, beta q, PQ, comma beta q is equal to 0. So this is the q, comma beta q point. Beta q is continuous, strictly decreasing, and convex. And beta q is commonly called the temperature function of the thermodynamic formalism that arises in multifactorial analysis of probability measures. So here I'm going to show you how quantization dimension is connected with temperature function. Now, in this case, how to calculate the quantization dimension. So notice, if q equal to 0, then we know here p of q, comma beta q equal to 0. Now take q is a real number. Okay. Now take q equal to 0. Then p of 0 beta 0 equal to 0 implies, now if you plug this here, from here, what we get? We get j equal to 1, Sj beta 0 equal to 1. That means beta 0 is equal to Hausdorff dimension. See that how they are connected, quantization dimension and pressure function, how they are connected with the Hausdorff dimension. Okay. Now next, p of 1, 0 equal to 0. How? If you plug this in this expression, say in this expression, so p of 1, comma 0, if you take t equal to 0 and q equal to 1, then we get q1, 0, 0. So we know for a given q, there exists a unique number for which 0 comes, so that we can say beta of 1 equal to 0. Let R is a positive fixed, R is fixed, then the quantization dimension kappa of mu is given by, this is the formula we have shown. The quantization dimension is given by this kappa. Kappa satisfies this one, and kappa is equal to quantization dimension. Now we are comparing with that pressure function. If q are equal to this number kappa over r plus kappa, then pqr, comma rq are equal to 0, because we put it here. This is the function. This function is this one. Thus, comparing the equations, we can say beta QR equal to RQR. Now look at that. Kappa equal to RQR 1 minus QR, which is equal to beta QR 1 minus QR. That means quantization dimension is connected with the temperature function that arises in multifactorial analysis. This beta is calculated by several authors for last several years in the multifactorial analysis, multifactorial formalism. Later, when we calculate the quantization dimension, we have seen quantization dimension. Okay, quantization dimension is calculated only few fractal probability measures, but multifactorial analysis was calculated for many fractal probability measures. And we have seen if the quantization dimension exists, that is equal to this number. So this is a connection. But quantization dimension is still not known for many fractal probability measures. There are lots of unsolved problems. Okay, this is one direction. Now, I am going to tell you something different. Okay, here, okay. So we see so many relations with quantization dimensions, like how beta is connected. Now, here is the definition. So this is the beta Q curve. This is the y equal to RQ curve. Now, you join this point, and we know beta 1 equal to 0. Now if this line segment where it cuts the y-axis, this is the quantization dimension. To determine dr, first find the point of intersection of y equal to beta q and the line y equal to rq. Dr is the y-intercept of the line through this point. And is it true for all probability measures, factor probability measures? We do not know yet, because we have seen only few cases we have calculated quantization dimension, and we have seen this is correct. But for the general result, this is not known yet. For general probability measure, fractal probability measure, I'm saying. Okay, now later, okay, what is the stretched Sierpinski triangle? Later, we have generalized the results of Graf and Luschke, say in this case. Okay, stretched Sierpinski triangle. Look at it here. This is we know Sierpinski gasket. Sierpinski gasket, there is no gap. Here it is called stretched Sierpinski triangle. So we have three mappings, similarity mappings. So first you apply, these are the three mappings, S1, S2, and S3. When you apply S1 on this whole triangle, everything is coming here. This gives S2, then gives S3. Keep trying, keep applying this one. Then eventually we get a limit set, which is called stretched Sierpinski triangle. Okay, and we are defining the probability measure P like this way. So 1/3, 1/3, 1/3. Now look at that. Here, this P can be defined many different ways by changing 1/3, 1/3, 1/3. Make sure the sum is 1. Of course, probability is a probability vector. Then we do not know the answer. Only we have calculated if P is a uniform distribution. That means probability is same over all these three triangles. Like this one, 1, 2, 3, 1/3, 1/3, 1/3. Then when you divide it the next stage, so there are 9 triangles, right? 1/3, 1/9, 1/9, 1/9, 1, 2, 3, 4, 5, 6, 8, 9. Yes. Then we calculated quantization dimension. Here it is. Look at that here. If beta is the Hausdorff dimension of the stretched Sierpinski triangle, then this is the formula, standard formula. We know beta is equal to 1 for the stretched Sierpinski triangle. And moreover, if P is the self-similar measure generated by the similarity mappings Sj associated with the probability vector this, then we know Hausdorff dimension of P equal to packing dimension of the measure P is equal to this. Who did this one? Given by Moran and Ray in 1997. Thus, we see that Hausdorff and packing dimensions of the probability measure supported by the stretched Sierpinski triangle are also obtained as 1. We have shown quantization dimension is the probability of this probability measure P that we defined is 1. Thus, in this case, all dimensions coincide, but quantization coefficient does not exist. This one is calculated only for the stretched Sierpinski triangle. As I told you, there are many triangles, many things still we do not know. And also, this probability P is defined by taking 1/3, 1/3, 1/3, and we can also change this vector. The answer is not known yet. Now look here, this Sierpinski triangle. We know quantization dimension is given by this formula, log 3 over log 2, by Graf and Luschke, but the optimal sets are not known yet. So this is also the unsolved problem, how to calculate the optimal sets. Now, so far we have discussed about fractal geometry. Now we are going to define about quantization about absolutely continuous probability measure. Here, Joseph Rosenblatt, he's a professor at University in Urbana-Champaign. He's retired, but he's still active. He teaches there. And in 2018, and we wrote this paper. See that, suppose you are driving on this road. So this is your highway, say freeway, you can say. And this is road, I'm giving equally importance. You are listening me, right? All of you? Any question up to this so far?
Yes, sir. We are enjoying.
Okay.
Yeah.
Okay. So this is the, now suppose you are driving on this road. Now forget about fractal geometry. There's no fractal geometry here. Okay. Now the general formula. You are driving. Of course, our highway safety is very important. So that when you are driving, for example, always make sure, suppose you are driving in a remote area, make sure your cell phone is always works. so that for any emergency, suppose you are falling into an accident, you need to call emergency, so that you make sure your cell phone always works. That's why when in the remote areas, suppose you are driving in a mountain, make sure your cell phones or anything, whenever you can get any help for you can contact emergency for emergency reason. Okay, suppose you are driving, this is a highway, and equally important. I'm not saying that this is this side is more important, this side is less important. That's why probability is defined here. Probability gives you the importance. Now, if you install one, say, cell phone tower, of course, this is the middle point, center. It is true always. And if you do not know anything, still you can guess the middle point here. And now, if you put two towers, so that we can get signal in our cell phones, then of course, then this will be in the diagonals, and it will be these 2 points. And you divide 1/2, then take expected. This, of course, this point must be expectable in its own region. And this, I'm saying average, expected conditional expectation. And 3 towers, look, 3 towers are like this. Of course, you can move this. In fact, there are in many locations, in many locations. And you see that if you increase the number of towers, the circle is increasing the diameter of the radius of the circle, and eventually it goes to infinity. If you put lots of towers, increase the number of towers, it coincides with the own circle, with the own region. Okay. Now, can you tell me what is the quantization dimension for this circle? It is 1, because dimension of the circle is 1. So quantization dimension is not interesting. You don't have to calculate anything. It is not a fractal, as I told you before. Quantization dimension for fractal geometry is very important, but for the other things it is not important, because we easily can figure out. Okay. Now, but we have shown it by mathematics. Okay. Now, how to calculate the optimal sets? We have shown alpha n of set of optimal locations is given by this formula, and the points alpha n lie on this circle. So this is the equation of what is the equation of this circle? Here it is. Depends on n, of course. And quantization dimension, this is the quantization error. If you know the points, of course, it's easy to calculate the error. Vn is the error.
There should be a restriction of keeping the minimum distance between the towers. No? Hello.
Restriction.
Because it may overlap, na? That's why.
No towers. No tower. Okay. So suppose 2 towers. So how to put it? Uniform distribution. I'm talking about uniform distribution.
Uniform distribution, it's okay. Say 2, 3, 4.
4.
Right.
Yeah, 2, 3 towers. So this tower will cover. So you divide here. So this divide. So this part, this part it will cover by this tower, and this will cover this 3 parts, right? This tower will catch. So
But,
we are dividing.
It depends on that. It depends on that conditional probability what you have shown. No.
Yes. Of course, this point, yes. This, if they are optimal location, they must be the conditional expectation in their region, because tower. What is the goal of a tower? Tower, like our closest location. So if you have the cell phone, they will look for the closest tower, right? So like that it works.
Sir, one question here.
Yes.
Whether this locations ultimately depends or not on the strength of that tower. How powerful those towers are.
Okay. Suppose you are right. Suppose all the towers have the same strength. Otherwise, it is not true.
But it cannot be true. But some may be.
No. I'm saying all the towers have the same strength.
Okay. If the strengths are different, then this will not work.
No. Then it will not work. This theory. Then we have to give a new theory. Then. Okay.
Yes.
Okay. You're right. Thank you. That's why I'm saying. Also, that weather condition is same, because suppose one side there is a storm, then maybe this tower will not work much, right? The strength will decrease, right?
But how the signals move, whether it moves, it does not. It should not depend on what is called weather condition. How it is depending on.
Okay, I'm not sure. Suppose I'm saying, sometimes people say there is storm weather. For example, when I call to India, sometimes we cannot get the signal to talk to my relatives, because I have to call several times. It disconnects. Then I tell what happened. Then they say there is lots of storm here going on. There is raining. That means then I understood. Maybe it depends on the weather. Make sense?
They are not getting the signal properly. That is the thing. Okay.
Yes, they are not signal. Yeah. Then I told them why. What is the reason? Then they say lots of tower storm is going on. Lots of things.
You are considering the ideal case, correct, na, sir?
Yes, I'm saying there is nothing change in the weather.
Ideal case.
Yes.
Okay.
Okay, I'm not sure because whenever there is a storm or anything, I see there is signal disturbs. Okay, okay. Okay, so this is the error and this is the quantization dimension. This is the formula for quantization. See that one is coming, I told you, and quantization coefficient here is a positive number anyway. Okay, now next, now look at that. This is interesting. In 2019, Gabriela Pena is my master's student. She is now a faculty member in a college. Now, Dr. Rodrigo, my colleague, it is me, and Dr. Suventas. So Dr. Rodrigo works in data compression, and Dr. Suventas works in applied mathematics, numerical analysis, and Dr. Shuajo is in some integral transformation. So see that all these other three professors are working from different regions, but still they can work in quantization. You know why? Because it is like a common idea. There is no you don't need any background. You can, if you have some ideas about math or calculations, everybody can work in this area. And unbelievable, you see this paper is published now in a well-known rank A journal according to Simago journal ranking. Yes, it is Journal of Optimization Theory and Application. These simple things are published. Now you think so important these results are. Now look, suppose you are driving. So now here our roads are circle. Now here our roads are semicircle, uniform distribution I'm considering. Okay. Then if you put one tower, this is the tower location. So what is this? This is the expected value of this region, of this lines, not the region of the line. This is one line or this line. If you put two towers, so it's the middle line. I'm saying uniform distribution, so you can easily guess the two towers will be, you divide in the middle. One tower here, one tower here, and then three towers like this, four towers like this. Now see that here, 1, 2, 3, 4, 5. 5 towers. Starting from 5, how the power towers are located. Remember, the goal of the tower is to cover maximum area within a shortest distance. Maximum area within a shortest distance. So one tower must be in the corner. This tower will catch some part from here, some part from here, and one tower here in the corner, like this. And the two towers will be here. It is uniform distribution. So this you can easily guess that one in the middle. Divide this region two parts. One is conditional expression here, conditional expression here, and this is here. Now 1, 2, 3. Now if you have here, it is 5, 6. 1, 2, 3, 4, 5, 6. So 7. Now see, the 2 points are always coming from the corner. Then some points are coming from the top, some points are coming from the bottom. Now suppose here this picture is for like 9 towers. 9 towers. Now to make sure, we always get 2 points coming from the corner. Then how many points are coming from the top and how many towers are coming from the bottom? That is the important things. Suppose you would like to install, say, 500 mobile towers. Now, can you tell me how many towers will come from the top? How many towers are coming from the bottom? That is the key things here in this result. I'm going to show you. Define how to calculate this. So suppose K, what is K? K means how many towers are coming from the bottom. So in this case, K is 3, right? If you know how many towers are coming from the bottom, then you can easily distribute the towers. Okay, how to calculate this K? Define the sequence AN such that AN is this. So AN is this one, this sequence. Now define the algorithm. Suppose K, as I told you, K means the number of towers which are coming from the bottom. If K equal to 1, go to step 4. Okay. So what is V of nk minus 1? Suppose, so V and K means when we are calculating the error for n towers under the condition K towers are coming from the bottom. So we set up this algorithm. Okay. Remark. Now look here. How to calculate the now. So if you know this algorithm and if you know this sequence, how to calculate the towers. So suppose you want to install, say, 40 towers. Now I'm calculating AN equal to AN. What is the AN? Say N is 40. From this sequence, we get AN equal to 16. Okay, so K is 16. Start the algorithm with K equal to 16. Okay. So AN equal to 16. So if you put K equal to 16, then if you use this algorithm, we also end up with K equal to 16. That means for 40 towers, 16 towers will come from the bottom. Let's take this example. This will be more fun. Say 2,500 towers you need to install. So I'm putting AN equal to 103. So I calculate AN from this sequence, which is 1035. Now I run this algorithm. Then I get K equal to 1042. See that very close. You do not need even a computer. You can just use calculator. See that we end up with K equal to 1042. So that means in the 2,500 towers, 1042 towers will come from the bottom. Then you can easily distribute the towers. Now for 5,000, the k value is 2083. See that an is 2071 and k is 2083. So this sequence and algorithms works very quickly. We don't have to wait. Do not have to run the algorithm for a long time. You can use just a calculator. Okay, so this is the way. This is the techniques. So we figure out it is correct. Okay, now, okay. So far we have discussed about the lines, roads, right? Now suppose we are going to discuss about the region now. Now forget about fractal geometry, forget about the lines. Now our goal is to install the mobile towers in a region. So this is the region. Suppose our region is a triangle. Suppose say UP, or UP is like a triangle. Of course, UP is not a triangle. It's not a circle. So it's not a straight line. Okay. Suppose it is this is a so simple case we are doing. So who is Carl Detman? Carl Detman is a professor of applied mathematics. He's a full professor of applied mathematics of University of Bristol, one of the top 5 universities in UK. So one day I was giving a talk in a conference like this, like I'm giving talk, and he was in the audience. Then when I gave the talk, he was so interested in this area. Then we started. It was face to face, of course, not virtual. And then we started discussing after in the middle of different talks, and after the talks, we start discussing. Then we got this result. Okay, what is it? This is the region. Suppose our state looks, or our country is a triangle, and we would like to install 2 mobile towers, and the distribution is uniform. So we are moving. So our goal is what? We are moving in our country, any place we can go, and our goal is to find the location of the 2 towers, so that if we move around our country, we can get the best signal in our cell phones. Look at here. What is the formula we got? If the triangle delta is partitioned into an isosceles trapezoid and an equilateral triangle, so isosceles trapezoid and an equilateral triangle, in the golden ratio, this, see that now golden ratio is again coming. Golden ratio is connected with many different research, but here also golden ratio works. Then the centroid of the isosceles trapezoid and the equilateral triangle form an optimal set of 2 means. We have proved it. Now, how to calculate 3 towers? If the uniform distribution on the equilateral triangle with vertices this and this, the set this is the only optimal set of 3 means. The 3 means in this case form an equilateral triangle having the sides parallel to the sides of the original triangle. You see that? So these are the 3 towers. P, 1 tower. So this covers this region. See that? It's uniform distribution. So you can see some symmetrical. This is one region, Q. Now 4 towers. The points this form an optimal set of 4 means. Due to symmetry, there are 3 optimal sets of 4 means. Okay, so P covers this region. See that this shape, and Q covers this region. R is this one. S covers this one. Now see 7, 8 towers. We have calculated this using Mathematica. There are lots of equations. If you increase the number of towers, number of equations increases. And so it is difficult to calculate. So we have just calculated up to 4 means. Then, okay, suppose if you give these problems to an electrical engineers, if you tell them, okay, how to install 20 mobile towers, what they will do? They will start running the algorithm. Professor Detman, he's an applied mathematician, and he also expert in the numerical things, and he put this algorithm in the computer, and he kept his computer running like almost a month. Then he told me, Mrinal, my computer is still running. Now I need to stop. I cannot keep my computer busy so long. Then he stopped the computer. After he stopped the computer, he got this configuration. Now look at that. Say, for example, say for 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Say 8 mobile towers look like this way. 9 looks like 10, 11, 12, like this way. Now, do you think this location is optimal? No, because computer did not stop. Computer is still running. So if you give these problems to the electrical engineers, they will also end up with this kinds of figure. But this is not exact locations again. So we gave some conjectures from this picture. For most n, there is an optimal configuration with at least 1 line of symmetry. In the previous figure, the line of symmetry is chosen to be vertical. In each case, the number of points on each side of the vertical line is equal. However, for n equal to 8 and 19, okay, here 19. Okay, 1, 2, 3, 4, 5, 6. I think 19 is this one. Okay, if you see somewhere for n equal to, in most cases we have seen there is a symmetry, but for n equal to 8, let me show you for n equal to 8. So 1, 2, 3, 4, 5, 6, 7, 8. You see that there is a line of symmetry, but here the symmetry is disturbing. See that this point is little down. But here there is symmetry. See that there is symmetry. There is in most figures there is symmetry. But in some cases symmetry is disturbed. So this is the way. But this problem is also unsolved. We do not know what are the exact locations. Up to 4 we have calculated exactly. So that's all I would like to tell you. And this is my references. So that is the paper that I told you. It came in Journal of Net Theory Applications in 2021. Very recent papers. All the results are recent. 2017 and 2020. All of my results are some new results. There is still many unsolved problems. Okay, any question?
So if there is some question, please.
It's fine. Very informative.
Very interesting topic.
Very interesting information.
Uh-huh.
What are the other applications, sir, other than mobile tower locations?
Okay, wonderful.
Finding...
Okay, there is a nice question. Why, one thing, National Security Agency does not give grant to all mathematicians. They only provide fund to them if they think it is interesting for them.
Correct.
National Security Agency gave me money for 2 years, and they gave me 2 months summer salary, all kinds of travels, research support. And now, according to them, I am a senior researcher. Then they are very happy on my research. But for the senior researchers, as you know, there is a funding problems. They stopped giving grant to any senior researcher. So they said, in future, if it opens, then they will consider me again. Okay, why they gave me grant? Because they like this research. They think it has lots of applications in security agency. How? United States has lots of missile stations. I'm not saying a lot, maybe few of, let's say 3, 4, or 5 missile stations around the country. So, and there is secret where they put the missile stations. Of course, some of them we know in Kuwait area, I think there is one army missile stations. So that if any wire comes, they can shoot missiles. Do not think like this. When there are United States do wires, like sometimes there is lots of wires. They do not shoot missile from United States. They shoot missile from some other country, right? They have the army stations. So how they determine the army stations? For example, say they give some importance to the countries. How much the countries are dangerous. For example, maybe say there is a country named X. I do not like to say what is the name of the country. And they think, how dangerous is it for the United States? They'll think, okay, this is 90% dangerous for United States. So give us probability 90%. So 9 over 10. Then maybe this country is not much dangerous. So put 1 over 100. Like this, so total probability comes 1. After that, so see that this is not uniform. This probability is not uniform now. Then based on this probability, they calculate what, say they want to put 5 missile stations or army stations. Then they calculate the 5 locations, optimal locations. Make sense? Good. Optimum is the best guess. Then they figure out, okay, this location is the best locations. Then they look near around that center where they can put the missile stations. Make sense?
Good. Sure.
Yeah. So it has. It also helps you to understand, to calculate where to put the best location, so that we can shoot the missile quickly without not taking much delay. Right.
Sir, another thing is that why you are considering always the triangles there? Because in
we do not answer. General question, we do not know. This is easy. Easy. Triangle is easy.
Okay.
Easy.
Even in fractal, you see the maximum they use the triangle. Number 2 is that in every case you are uniform distribution you are considering. No?
Okay, yeah, you can consider any distributions. I'm taking uniform because it's easy to handle. If you take it any other distributions, we do not know the answer. How to calculate it?
Okay. Still open.
That is a challenge, great challenge. That means another challenge.
You see that all of the results, see that 2021, then 2020. My results all are
just starting.
Yes.
Yes.
All 2017. This is coming Journal of Fractal Geometry. 2018. These are all completely new. Now, one thing, when I was giving talks in many other places also, and they asked me questions. Look, in the case of fractal geometry, we are always considering open set condition. That means when you apply the mappings, all the image points are image set they are not overlapping, right? Then when I was giving a talk, then some professors, many professors, they are asking me questions. Did you solve any problems without open set conditions? Suppose the image sets are overlapping each other, then the answer is not known yet. Recently, myself and Carol Simon, I think you know him. He's a well-known mathematician also from Budapest, and we started discussing working on overlap case. Hopefully, in the near future, we'll come out with some new techniques in how to handle overlap conditions, and this will generate also many new open problems. And of course, I'll inform all of you. And in this figure, I would like to tell you that, as you have seen, you do not need to know enough background. Do not need, if you want to do some new research, and this is a good area of research. And this is not my PhD or postdoctoral research. When I was assistant professor, visiting professor at the University of North Texas, just for 1 year, then one professor introduced me this area. Then I saw this is really interesting, because I like to do work in some interesting area where easy to get grant and people will like, and I like that. So I switched my research.
Sir, I want to say one thing. Even though there is a uniform distribution, but whatever you are talking about overlapping,
yes,
right now we are overlooking the overlapping. Overlapping will be there a little bit, certainly.
In the fractals, yes. In the fractal set, yes.
Yeah.
Fractals.
Say your mobile tower signals, that will be overlapping at the boundary. That
no, I'm saying no. The mobile, there will be some overlapping.
There will be intersection. That is why on those
yes, boundary line. Yes, intersection. Yes, boundary line.
There is what is called error in signals.
Yes. Yeah, there is some overlapping, but
now it is minimized. It is minimized now. We do not generally get such cases.
So any other question, please? I think.
Hello, sir. I have a question.
Yeah, please.
Yes.
Sir, when you have said that you are talking about that optimal location of the what you are saying, or location of the towers in case of roads. That next.
Yes. Here, right?
No,
can you see
the next. Yes. The next what you have said, right? Semicircle type things, right.
Yes. This is uniform distance. This is here.
Yes. So in this case, in the next page, you have shown that you have calculated that n. This, right.
Yes.
So what is special about this sequence, n equal to this? Why you have chosen this sequence?
You know one thing, I calculated for 4 points, 5 points, 6 points, 7 points, 8 points.
Okay.
Like manually, I was calculating with the computer, like 100 points.
Okay.
Then I came out that say, okay, first with these algorithms, I was calculating, and I have seen those exact numbers are false closest to a sequence, like this sequence.
Okay.
Trial and error method. Actually,
trial and error method.
Trial and error method.
Okay.
Now by trial and error method, I've seen, I put all the numbers, then I've seen closest sequence, I got this one. I think there is an encyclopedia of numbers. Okay, if you don't know that, it is encyclopedia of numbers, and if you put numbers there, then they'll give you a closest sequence.
Oh, okay, I see. Thank you.
So this is interesting.
Yes. Thank you.
Yeah. Okay.
One more question, that the region you have taken circular, that may not be exactly circular or semicircular. If it is different, your answer, I think solutions will be different.
In the real life, there is no road, I think, like semicircle, right? I think in the real life, there is no circle, no road like this. It will be some oval shape or some way maybe closed, right? But we do not know the answer of those. So I'm saying, okay, suppose it is circle, then we get this answer.
Okay. In that
then
case,
suppose the road is this, we know this answer. Now suppose your country, say India is a triangular shape. Actually, is it triangular? No, it is not a triangle. It is not a circle. It is not anything. So we do not know the answer. We do not know. Even, one thing, suppose if you take this one to keep the two sides same and make the region, say one is semicircle, right? Semicircular boundary, right? Then we do not know how to calculate these points. if you deform a little bit
These are
this
all
triangle, you do not know. Yeah, these are all called unsolved, completely unsolved problems.
Eventually, it will be solved.
Yes.
And he will do.
Yeah.
Yeah. Okay, sir.
So let us give
Very
a
good.
big hand to Professor Roychowdhury
Good.
for a very nice and illuminative talk.
Yes.
Yeah.
And
So,
in this figure, I would also like to tell you, so with Carol we are working on overlap case. So if it is solved, then many open problems will generate. And other things, I am always easy access to the students and all faculties, everybody. Especially students are always scared of finding, right? Students are always scared.
Yes, sir. I've just thought that I'll use our master degree students in this area. You know, they are coming from the IIT. No, they're very
wonderful
guys in IIT. So
wonderful.
We'll use the IDD students. We'll use.
As I say, many open problems you will see. You do not need, sometimes. And also one thing, the students are scared of learning something like to communicate.
They like fractals. They like fractals. They are working on fractals, dynamical system, everything. So they will like it, sir.
Okay.
So there is a good scope. We can collaborate. If you wish.
Okay. Thank you. Sure, I'm also interested. That's why I'm saying if the students like, they can also communicate with me. I'm always easy access to everybody.
Sir, it is now becoming 9. 9:05. So I have to leave the department. I have to go to the.
Sure. It is the whole day.
Sir. Sir, please. আপনার সঙ্গে দেখা হলে দেবনাথ স্যারকে আমার প্রণাম জানাবেন.
Yeah, sure. Of course. যোগাযোগ রাখবেন. Keep in touch, all of you. Yeah. Thank you.
Welcome.
So please
keep in touch, sir. We'll keep in touch.
Yeah, sure. Thank you.
Thank you, sir.
Yeah, thank you. So how do you stop now?
Just stop.
Thank you so much, sir.
Sharing.
Thank you, Mega, and
Mega will help.
Anushika.
Thank you, sir.
Thank you, sir.
Sure.